Okay, here is practice test 3. For this first question, we want to determine if these functions are inverses of each other. We do that by doing the composition both ways. We do f of g of x and g of f of x. If they are inverses of each other, everything should cancel out and we should just get x both ways. So f of g of x means rewrite f of x twice our input minus 3. But now our input is all of g, f of g. So we plug x plus 3 over 2 into f, into the x. The 2's cancel. We get x minus 3 plus 3. Wrote that in the wrong order. Should say x plus 3 minus 3, but either way, that's x. Then we had to check it the other way, g of f of x. We plug all of f of x into this x in g. So that's 2x minus 3 plus 3 over 2. The 3's cancel, then the 2's cancel. Yes, we just get x. So yes, these two functions are inverses of each other. Okay, this guy, we're finding the inverse. First thing we do is replace f of x with y. Then we swap all of our x's and y's. Every x becomes a y, every y becomes an x. Our goal now is to get this y by itself. So we subtract the 5 over. Then to get rid of this cube, we take the cube root of both sides. On the right side, the cube root of junk cubed is just junk because they're inverses of each other. They just cancel out. We get this expression, this equation. Move the 3 over, and then finally rename y f inverse of x. Here's our inverse. The inverse of a cube is a cube root. Instead of adding 5 on the outside, we're subtracting 5 on the inside. Instead of subtracting 3 inside, we're adding 3 outside. And then we graph both. This is just graph transformations. F is just x cubed, move 3 to the right, up 5, over 3, up 5. F inverse is just the cube root, moved over 5 to the right, up 3. So here's F inverse. Okay, if the point 39 is on the graph of one function, then the point 93 will be on the graph of his inverse. All functions and inverses do are reverse all of our x's and y's. Okay, page 2. We want to find the inverse of this exponential function. The inverse of an exponential is a log, so we should get a log function. And there are a couple of different ways we could go about it. Either one's legitimate. Here, this is what I saw most people doing in class. It's perfectly fine. First, rename h, y. Swap all our x's and y's. So we get x equals 2 to the y minus 4. I'm trying to get that y right there by itself. So add the 4 over. Now I need to get this y down onto ground level. The only way to bring something down from an exponent is to take logs. This is what logs were invented for. This is why we do logs. So say I wanted to take the natural log of both sides. I'm allowed to do that. The purpose of taking this log is to use the rules of logs and move this exponent of y down to multiplying in front. Now, natural log of 2 is just a number, and that's multiplying the y. To get it to the other side, I just divide both sides by ln of 2, and I get this is my inverse, natural log of x plus 4 divided by natural log of 2. And I'm done. That won't simplify. I can't do anything with it. I could use change of base formula, but other than that, we're done. Or here, what I think is a better method. It's really the same method. I'm just going to use a different base. Since the base of my exponential was 2, instead of using natural log, I'll use log base 2. So I get to the same level, get to the same step, but now instead of taking natural log of both sides, I'll take log base 2 of both sides. I could use any base I wanted. I might as well use the base I already have. log base 2 of 2 to the y is just y. Those are inverses of each other. Log base 2 and 2 raised to an exponent are inverses. They just cancel out. And all that's left on this right side is just y. So I get y equals log base 2 of x plus 4. Rename y h inverse. And the inverse of this exponential function with base 2 is a log function with base 2. Instead of subtracting 4 outside, I'm adding 4 inside. Okay, writing an expression is a sum or difference of logs. Anything on top is a positive, anything on the bottom is a negative. All the exponents come down front. We just get this. Like that should be relatively obvious. Same thing in this one. Anything on top that's multiplied inside becomes added outside. Divided inside becomes subtracted outside. Anything on the bottom will be negative. Anything on the top will say positive. Okay, I can't distribute a log. This is not log base 5 of x minus log base 5 of 1. You cannot distribute a log. Okay, same game here, only now we're going backwards. Anything that's positive will be on top. All the exponents come in. Anything negative will go on the bottom. So the y and the m are negative. They're on the bottom. The x and z were positive. They're on top. This is even easier. I've got a couple of things added outside that becomes multiplied inside. And you could leave it like this. This is perfectly fine. Or you could FOIL x minus 1 times x plus 1 and get x squared minus 1. Okay, next page. We're evaluating logs. The answer to a log question is the missing exponent. The question here is, what power would you put on 2 to get 16? And the answer is 4. That's it. That's all you write. The answer is 4. Because 2 to the 4th power is 16. That's the reason, but this is the answer. Log base 3 of 1/9 is negative 2. 3 squared is 9, but I've got a 1/9. Remember, a negative exponent means you move down to the bottom. So log base 3 of 1/9 is negative 2. But logs can't be negative. No. You can't take the log of a negative. The inside can't be negative. The answer can easily be negative. Log base 25 of 5. What would you do to 25 to get 5? You would take the square root. Square root of 25 is 5. Square root written as an exponent is 1/2. So 25 to the 1/2 power is 5. What about number 12 here? Log base 9 of 1. Log of 1, any base, is always 0. Doesn't matter what your base is. That's one of your rules of logs that everybody now has memorized. 9 to the 0 power is 1. Doesn't matter what the base is. Log of 1 is always 0. What about log base 4 of negative 2? You can't do that. You can't take a log of a negative. The argument, the inside is not allowed to be negative and is not allowed to be 0. You can't take log of 0. Your answer can be 0. The inside can't be 0. Okay, writing in exponential form. So this is log form. This is exponential form of the same information. The base raised to the exponent equals what's inside. 3 to the 4th power equals 81. Okay, going the other way. This is exponential form. 6 squared equals 36. Our base is 6. The answer is the exponent when we're writing in log form. And the 36 goes inside. Log base 6 of 36 equals 2. 6 to the 2nd power equals 36. Okay, page 4. Solving some exponential equations. We have two different kinds of exponential equations. The ones where it's easy to use the same base on both sides and the ones where it's not. Number 17 is the first kind. We can use the same base. We can use a common base of 2. 2 to the first is 2. 2 cubed is 8. So I've rewritten 8 as 2 to the third power. Then I have to distribute this 3. Remember, a power raised to a power we multiply. So 3 times 2x minus 5 is 6x minus 15. Distributed the 3. Now I can set the exponents equal. Now that I have the same base on both sides, the exponents must be equal. I get this linear equation. It's really easy to solve. We get x equals 6. Number 18 is more complicated. It's very difficult to write 3 and 5 as powers of the same base. It's possible. Here's your answer. But it's not easy. So we don't try that. We take logs of both sides. And I could use any base I want. I chose to write natural log, honestly, because it's less writing. So I take the natural log of both sides. The whole purpose of taking logs is to bring the exponents down to ground level. So this 2x plus 1 comes down and is multiplying ln of 3. Same with the 4x plus 6. ln of 3 and ln of 5 are just numbers. They just distribute. So 2x times ln of 3 is not ln of 6. I can't take the 2 times the 3. ln of 3 is just a number. It's just going to hang out. So distribute the ln of 3. On the right, distribute the ln of 5. Now I have 4 terms. 1, 2, 3, and 4 terms. 2 of those terms have x's in them. So I'll move this 4x ln of 5 over to the left to be with his buddy. And I'll move the ln of 3 that has no x in it over to the right to be with his buddy. All the x's are on the left, all the non-x's are on the right. At this stage, we always do the same thing. Factor out that common factor of x on the left. And now I've got this number, 2 ln 3 minus 4 ln 5. That's a number, multiplying x. To get rid of it, we divide by that number, and we get this. This nasty looking fraction is our answer. It won't simplify. We could type it in a calculator and approximate it, but no rules of logs are going to make it look any prettier, so we just leave it alone. Okay, now we're solving log equations. We also have two kinds of log equations. The ones where everybody is a log, like number 20, and the ones where not everybody is a log, like number 19. So number 19, this 2 is not a log. My goal is to squish all my logs together on the left side, write this as log of stuff equals a number, and then convert to exponential form. So on the left, subtracted outside becomes divided inside. Now I've reached my goal. Log equals number. We convert to exponential form. 4 to the second power equals what's inside. 4 to the second is just 16. So we have x over 9. We get rid of the 9 by multiplying. We get x equals 144. We have to check and make sure that's allowed. So we plug 144 back in. We're not taking log of 0 or a negative. We're okay. Okay, over here on number 20. You cannot just go through and cancel the logs. That's the most common mistake made here. Don't just go through and cancel the logs. I need to make this look like 1 log equals exactly 1 log. 1 log on each side. So I need to combine these logs into one single log. Added outside becomes multiplied inside. Now, here in this step, I have log equals log. Now I can set the insides equal. This is a quadratic equation. We spent weeks solving quadratic equations. I promise you, you will know how to solve this. In fact, it's pretty much guaranteed it's going to factor. But in order to factor, I need to get in standard form. I need to get everything onto one side. So I'll FOIL out the left side, move everything to the left side to get in standard form equals 0. And then I factor. This factors x minus 9, x plus 2. I get two solutions, x equals 9 and negative 2. But I must check my solutions in the original equation. Okay, if I plug in a 9, I get log of 6. That's fine. I get log of 7. That's fine. And let's see, that'd be 18 plus 24. That's positive. That's all I care about. 9 is okay. If I try negative 2, though, negative 2 minus 3 is negative 5. I can't take log of negatives. That negative 2 is no good. Okay, number 21, we are sketching a graph of this exponential. Our base is 4. That's bigger than 1, so we'll have exponential growth. My a that's in front here is just 1, and I'm shifting everything up 2. So normally I would have a horizontal asymptote at 0. Because of the plus 2, everything gets shifted up 2. So I have this horizontal asymptote at y equals 2. Normally, without the plus 2, this graph would pass through the point 0, 1, but now everything is shifted up 2, so we'll pass through 0, 3. And there's a rough sketch of the graph. And the last page, number 22 is pretty easy. I give you the time, just plug it in for t, time. So 1000 e to the 0.21 times 10. As long as you plug that in your calculator right, you'll see you get 8166.17 bacteria. Number 23, we're doing radioactive decay. I want to know the half-life, meaning when I have half of my initial amount. How much do I start with? I start with A sub 0. That's my initial amount. So after a half-life, I have half of that remaining. I have half of A equals to the function. Those A's cancel out, so I get a 1/2, which is just 0.5, equals e to the negative 0.31t. That's an exponential equation. To solve it, I take the natural log of both sides. Since I'm dealing with base e, I should use natural log. So I get natural log of 0.5 equals natural log of e raised to the stuff. E raised to a power and natural log are inverses of each other. They cancel out. That's what inverses do. So we get ln of 0.5 equals negative 0.31t. Trying to solve for t, so we divide both sides by the negative 0.31 and we get this expression. Just throw that in our calculator, ln of 0.5 over negative 0.31, you get 2.24, whatever our time unit is here. Hours, days, years, whatever. Number 24, we have natural log of 12. I need to write 12 as some multiplication of powers of 2 and 3. So 12 is 3 times 4. Rules of log say I can break that up as ln of 3 plus ln of 4. Multiplied inside becomes added outside. 4 is 2 squared, and I can bring that exponent down in front, so I get ln of 3 plus twice ln of 2. ln of 3 is what we called v. ln of 2 is what we called u, so we get v plus 2u. Similarly here, on number 25, divided inside becomes subtracted outside. 9 is 3 squared, 4 is 2 squared. The exponents come down front. So I get 2 ln 3 minus 2 ln 2. ln of 3 was v, ln of 2 was u. We get 2v minus 2u. And that is it.